Okay, before we start talking about composition of functions, which is what we are going to do today, we're going to use composition of functions to confirm whether or not functions are inverses. We are going to go through a couple of examples like the stuff you guys did on your homework last night to look at what we do when we have something like this, which is a domain restriction. Okay, so when you have a even polynomial, you will sometimes see a domain restriction on the polynomial when we're finding inverses. So the reason that we see that is that x to the fourth looks like this. It's a u. And this x is greater than or equal to 0, what that does is that gets rid of the negative side of the u. So instead of a whole u, we just have half. That is a domain restriction. I have restricted the domain of that function. It is usually all real numbers, and I have said I'm only going to look at numbers between 0 and infinity now. When we go to find the inverse of this function, that's y equals 1/3 x to the fourth, and then we switch x and y, and we solve for y. So multiply by 3, and then take the fourth root of both sides. Now when we do this, we have to remember the plus or minus. So I have plus or minus fourth root of 3x. And in class yesterday, we learned that that plus or minus gives us two pieces. We get a positive fourth root of 3x and a negative fourth root of 3x. Now, in class yesterday, we also learned that inverses are reflections over the line y equals x. And so if you look at the line y equals x, and you look at the two graphs we have, you'll notice that the pink graph and the green graph are not reflections of each other. There's a problem. My pink graph is half of the green graph. And so you ask yourself, well, how can I make the pink and green graph reflections of each other? How can I make sure that what I'm looking at are actually inverses? And the answer is that we eliminate one of the pieces. And the piece that we're eliminating here is the negative piece, because that is the piece that is not a reflection over the line y equals x. If you reflect the pink graph over the line y equals x, what you get is the top piece of that green graph right there. And so our inverse is y inverse is equal to the positive fourth root of 3x. Now, I had an indication that I was going to use the positive root and not the negative root, and that's because I was looking at positive values of x right there. So this x is greater than or equal to 0 translates specifically to me choosing one of the roots when I took the even root. And in fact, when you start with a domain restriction, you must choose a root. So either the positive root or the negative. All right, so if we start with a domain restriction, which is what we started with here, then we are going to have to pick a root at the end, either the positive root or the negative root. Now, this goes the other way as well. So I started with a fourth root polynomial here, and if I look at g of x, I'm starting with a root. And so if we look at that function there, g of x, That is a square root function that has been reflected over the x-axis. It's also been moved left 4, but it looks like that. Now, when I go to calculate the inverse algebraically, I switch x and y, and then I solve for y. And what we do here is we square both sides. You get y plus 4 is equal to negative 1/2 squared is positive 1/4. So this is 1/4 x squared. And y equals 1/4 x squared minus 4. And that is a quadratic. That is a parabola right there. It's a parabola that has a vertical dilation of 1/4, and it's been moved down 4 units. And if I graph it, it's a wide parabola, but it's a whole parabola. And so again, we look at that and we say, well, if I draw the line y equals x, the pink graph and the green graph are not reflections of each other over the line y equals x. One of the pieces of the green graph needs to go. So you wonder which piece needs to go. And it's a little difficult to see with both of them there. So you can draw yourself another picture. There's my pink graph. And if I draw just the right side of the green graph and draw my y equals x, it's really easy to see that those things are not reflections across that line. If I folded my paper on this purple line right here, those are not reflections of each other. If I draw the left side and draw my line y equals x, then it still looks a little funny, but those are reflections of each other. And in fact, there was an indication at the beginning of the problem that I was going to look at the left side of my parabola, and that indication is right here, that negative right there. So what I say in this case is y inverse is equal to 1/4 x squared minus 4 for x values that are less than or equal to 0. And so this negative right here translates directly to negative x's. Okay. All right, so we are going to talk about composition of functions, but before we do that, we are going to review what we know about function inputs. So if I'm given the function f of x equals 2x plus 1, and then I want you to find f of 2. What you do is you take the 2 and you put it in where the x was. So 2 times 2 plus 1. And so f of x simply means my function f has an input of x, but I can use an input of anything I want in that function. So in this case I use 2, and so that's 4 plus 1, which is 5. Now if I wanted to use y, I wanted an input of y, then I would say 2 times y plus 1, which is 2y plus 1. And if I wanted to, I could even put in more than one thing. So in this case, I'm going to put in x minus 4. So I'm going to use the function f, which is the relationship of 2 times something plus 1, and the something that I'm going to multiply by 2, in this case, will be x minus 4. So this is 2 times x minus 4 plus 1. And that's 2x minus 8 plus 1, which is 2x minus 7. I could also put in an x squared. So I say, all right, 2 times x squared plus 1, which is just 2x squared plus 1. And so what we've actually done for the last 2 problems is what we call composition of functions, where I put one function into another. So in this case, the function was x minus 4, and in this case, the function was x squared. And I put those into another function. Now, the way we write composition of functions is that we write it with function notation. So f of g of x, and we say that f of g of x. And what that means is I want you to put the function g into f as the input. And it looks all parenthesis complicated when you write it, but really we know what g of x is. We were told that g of x is the square root of x. So f of g of x is just f of the square root of x, which looks a whole bunch like the f of x minus 4 and f of x squared examples that we did. So all I'm doing is putting the square root of x into the function f, and the function f is 2 times something plus 1. So f of g of x is 2 times the square root of x plus 1, or just 2 root x plus 1. And that's composition of functions. I said use the function g. Use the function g as an input for f. And here's what the function g is. It's the square root of x. All right, guys, so we use composition of functions with inverses. Remember that yesterday we talked about inverse operations and how one operation undoes the other, and that's an inverse operation. So if I multiply by 3, the inverse operation would be to divide by 3. And remember that I said that functions work in kind of the same way, inverse functions, in that one undoes the other. And that's what we see when we use composition of functions to confirm inverses. So if 2 functions are inverses of each other, so if f of x and g of x are inverses, then f of g of x is equal to g of f of x is equal to x. And what that's saying is that if 2 functions are inverses of each other, when I use composition of functions, one way, I'm going to get x. So I put g into f, I'll get x. And then if I use it the other way, if I put f into g, I will also get x. That's what that equation means, right? And so we can confirm that functions are inverses of each other by using composition of functions. All right, so we can confirm that functions are inverses of each other by using composition of functions. What we're looking for when we do it is we're looking for an x at the end. So I use composition of functions, and if I get an x, then I'm talking about inverse functions. Now, this is important to do both ways. So remember at the beginning of the year when you had a system of equations and a point, and they said, is the point a solution to this system of equations? If you plug in the point and it works for the first equation, you still have to test the point in the second equation. You still must test it in the second equation. So you can't just assume that because the point works the first time, it's going to work the second time, right? The same thing is true for inverses. Just because you test it one way and get x, you still have to test it the other way as well. So we've got f of x is 2x plus 5, and g of x is x minus 5 over 2 we are going to test f of g of x. And so here, g of x is x minus 5 over 2. So what I'm really doing is I'm putting the x minus 5 over 2 into f as an input, right? And f is 2 times something plus 5. So f of g of x is 2 times x minus 5 over 2 plus 5. And then we simplify from there. So this 2 and this 2 cancel out. And I get x minus 5 plus 5, where your 5s also cancel out. So we just get x. And that's what we wanted, right? That shows us that f and g might be inverses of each other. I can't make a definitive decision about this yet, but they might be, right? That's what we wanted. Okay. And so then what we do is we go and we confirm the other way as well. We say, cool, f of g of x is x. This is good, right? But we need to confirm it the other way as well. So we say, all right, well, what is g of f of x? And so remember that f of x is 2x plus 5. So g of f of x is just g of 2x plus 5. And that is 2x plus 5 minus 5 over 2. And that's 2x over 2, which is just x. And that's what we wanted, right? That tells us that the functions f and g are inverses of each other, right? This is equal to x. And so because f of g of x is equal to g of f of x is equal to x, we can say that f and g are inverses. And in order to get credit for these problems, you need to show me all of your work, but you also need to state the inverse relationship here. So you've got to tell me, yes, these two functions are inverses of each other, and this is why. And the this is why is that f of g of x is equal to g of f of x is equal to x.